thank you everybody for resuming your places. I'm delighted to introduce the last talk of the season, and our presenter or speaker tonight is William Armstrong, resident of Armagh. He's going to present a talk on the Fucine Tunnel, and is detailed in the subtitle. It is indeed a fascinating tale of embezzling civil servants, cowboy builders, and not quite the eighth wonder of the world. So I'm happy to hand over to William.
Thank you very much.
Thank you.
I reckon this is possibly my 51st talk, or nearabouts. I've been coming to these from when I'm about this height. So it's quite fun to be on the other end of the Armagh Natural History and Phil Society. So, Fucine Tunnel. Ah, there we go. So the Fucine Lake was located in the middle of Italy, next to the Red Star, approximately 80 kilometers northeast of Rome. At the time, it was the third largest lake in Italy and the largest in southern Italy. It was approximately 150 square kilometers in area, and due to the local topography of the land, it was endorheic in nature. Now, that simply means the lake acted like a giant puddle. There were no natural outflow lets from the surrounding area, which meant that the water level of the lake was controlled solely by the processes of evaporation and water seepage. So this lake was eventually drained fully by Prince Torlonia. His project began in the year 1854 and ended in the year 1876. And his chief engineer, a Swiss man by the name of Brise, was responsible for recording all of the dimensions of the Roman tunnel in situ. So I'm giving them their kudos now before we get stuck in. To give you a bit of perspective on the enormity of this project, I have a quote by Pliny the Elder in Natural History. He says, "I indeed consider the tunnel dug through a mountain to drain the Fucine Lake among the most memorable accomplishments of the same Claudius. Although maliciously neglected by his successor, the expense was indescribable and the workers numberless. So over many years, because where the mountains were of earth, the soil from the channel had to be cleared through vertical shafts by means of winches, and elsewhere the rock had to be cut away. All of this great effort, which can neither be comprehended nor described, except by those who have seen it, took place in darkness." So this tunnel, once it was completed, remained the longest tunnel in the world for 1,800 years, until it was surpassed by the Frejus Rail Tunnel in 1871. So this is a print provided by the Swiss engineer Brise. This is included in his report, and it shows quite neatly the topography of the lake, causing it to be endorheic in nature. The local population around the lake were known as the Marsi. They were fishermen and farmers, but due to the steep banks, the steep slopes around the edge of the lake, they were forced mostly to the side, to the low level ground next to the lake. And when the conditions were such that the rains would flood the lake, the surrounding land would at times become inundated for up to 3 to 4 years. During this polytheistic time, the lake had its own god by the name of Fucinus, or Fucino, the same name as the lake. The trees surrounding the edge of the lake were also sacred to them, and this meant they couldn't be felled, which again constrained and compressed the population into this land around this low-level land around the edge of the lake. So they petitioned Julius Caesar. They petitioned him to create a tunnel or some form of project which would help drain the lake and ease their problem, ease the issues they were having. Julius Caesar was quite minded to help them in this, but unfortunately for them, he was assassinated before he could engage in this undertaking. So then it passed to Augustus, Tiberius, and Caligula. And all three in turn decided not to take on the project due to its expense. It was just too much, they couldn't handle it. As time went by, though, more pressure was built for the need of a good, stable agricultural base in the heart of Italy. Now, this was due to Rome having a population of 500,000 at the time. The center of Italy was going through an agricultural decline. So there was a growing need for the project to be undertaken. So that brings us to our good friend Claudius. And unfortunately, we don't have an image of Narcissus, but I managed to find a stone with his name and carved upon it. When the project was first suggested, private speculators came forward to offer the funding of the project in return for the gifting of the land that would have been uncovered by it. However, the Roman emperors hadn't really ingratiated themselves to the people at the time. There was a lot of love felt for Augustus, but Tiberius had been indifferent. Caligula needs little explanation. So the Roman emperors really needed some, or Claudius rather, wanted to develop some goodwill with the people. So he was persuaded by Narcissus that the Roman throne should undertake the entire funding of the process themselves alone. Narcissus had been a freedman who formed the core of the imperial court under the Emperor Claudius. He is described as in charge of correspondence. I'm not going to try the Italian. He had been Claudius's personal slave before Claudius's ascension, and so there was a great trust between them. So Narcissus was given total management of the project, which, well, we'll see how that pans out. So this is an aerial image showing the line of the tunnel. And the north point here lies within the basin, the Fucine Basin. Here we have Mount Silviano. Across here we have the Antonine Plains. And then down at the bottom we have the River Laris, which is where the tunnel exit. Well, this is where the water came out. So the reason they had to go for a tunnel was again due to the topography of the land surrounding the lake. On way over here somewhere, there was the potential for a canal to be dug through a low section of the mountain range. However, even at that, it was still far too expensive to attempt that. So they stuck with the tunnel. The tunnel measures 5,595 meters long. It was built in 3 sections. There was a gentle, in 3 straight sections with open angles to one another, following this line down to the River Laris. The point where it flowed into the River Laris was at the apex of a curve. This was just a benefit of the local ground to allow for a shorter distance to the tunnel. So just to give a little understanding of the methods used by the Romans when digging tunnels at the time, they were constricted by the air circulation that they could get down into the tunnel, the tools that they had at their disposal, and their ability to deal with the ingress of water. So, as shown quite neatly with this image, it wasn't possible for them to dig at 2 ends of a tunnel to meet in the middle and maintain a single gradient across the entire length of the tunnel. It would be all right on the lower section going up, but on the high section coming down, you would have the inevitable problem of filling of water. And as there were no pumps capable of removing large volumes of water at that time, what they would do instead is dig a tunnel following the line of the route they wish to follow, but they would dig above it so that they could maintain an outward fall in both directions. And then after they met in the middle, they would dig down until they reached their desired gradient through whatever obstruction they were trying to pass. However, in this case, the tunnel was too long. It was too large for them to do it as a single ended point, as a single dig in either direction. So instead, they had to go with a multi-shaft approach. Now, this would allow them to start the project in many, many locations along the length of the tunnel. And if any of the ground conditions that they were digging into had higher rates of water ingress, it would allow them to continue in other places and maintain a general flow to the project. Now, this is another plate from the Brise report. What you have to bear in mind when looking at this is that it has been massively compressed to fit it all in on the one page. So when you look at this image, there are 33 shafts in total. You have 22 on the western side of the mountain, and you have 11 on the eastern side. It's not particularly clear, but there were slightly sloping lines running down in these sections. These were kunukuri, and they were used specifically for ventilation, and in some cases beneath the mountain here, they were also used for the removal of spoiled material. The shafts on the western side ranged from 70 to 122 meters deep, and the shafts on the eastern side ranged from 17.6 to 22 meters deep. The lake bed was at a depth that was 21 meters higher than the elevation of the River Laris at the far side. So across 5.5 kilometers of distance, they only had 21 meters of fall to maintain across that entire length. So that gives you a 1.5 meters to a kilometer of gradient. So they were working with fairly tight margins. Interestingly, the tunnel entrance was placed over a meter above the elevation of the deepest point of the lake. Now, this indicates that the Romans didn't intend to fully drain the lake, and this would be indicated by this is probably due to religious reasons, such that there was a quote saying that the Marseille people did not want to eradicate their god Fucine entirely, but merely wanted to make him listen to reason. So, before undertaking a project of this size, it would have been necessary to do a large data gathering. Now, to do this, the Romans had some fairly impressive pieces of kit at their disposal. If we have any engineers here, I know they'll probably see some similarities between this, which is this is called the dioptra, and it was used for it was a leveling tool used for finding a level over large distances. And this is very, very similar in principle to what we would use today, the theodolite. The other piece of kit that they had was called the corybates. Now, this was essentially a 6.5 meter long board with a sight at either end and a channel 1.5 inch deep by 1 inch wide and about 24 inch, well, 2 meters long. And that was used, the channel with water was used under windy conditions. So when they had the water touching the levels at either end the whole way along the channel, they knew that their corybates was level. The other pieces of kit they had were 2 plumb levels on either end. And when these lined up with marks or a scale placed upon the supporting struts, they knew that their system was level. They knew that they were pointing in the right direction. We have another, I have another historical quote from Vitruvius who describes the types of leveling equipment used when explaining the supply of water to country houses. The first stage is leveling. This is done by dioptras or water leveling by the corybates. The last is the most accurate, since dioptras and levels are liable to error. The corybates is a straight rule about 20 foot long. At the very ends it has equal legs fastened to the rule at right angles. Between the rule and the legs are cross struts fixed by tendons. These have perpendicular lines accurately drawn and plummets hanging down from the rule, one over each cross strut. When the rule is in position, the perpendiculars, touching the marks equally, show the position is level. If the winds obstruct this, and if because they are moved about the lines are unable to give a definite result, the corybates should have on its upper side a channel 5 foot long, 1 inch wide, and 1.5 inch in depth. The water should be poured in, and if it touches the lips of the channel equally, we shall know that the position is level. So, the Roman engineers were able to get very precise measurements. They were able to make very precise measurements underground. We're all very familiar with the Roman aqueducts. But when we picture the Roman aqueducts, it's usually above water with the arches spanning between valleys. What I didn't realize is that most of the aqueducts are actually underground. So, from a technical perspective, they really knew what they were doing. So, our main source of information for the number of men involved and the time taken to complete this project comes from Suetonius. And he gives us a historical quote in his book, The Divine Claudius. He brought to completion public works, great in scale and utility rather than in number. The following are particularly notable: an aqueduct begun by Caligula, also a drainage tunnel for the Fucine Lake, and a harbour at Austria. These last two, to be sure, even though he knew the tunnel had been refused by Augustus to the Marsi, who urgently requested it, and that the port had often been considered by the deified Julius, but given up upon account of the difficulty. The Aqua Claudia brought into the city on stone substructures cool and copious water sources, of which one is called Corellius and the other citrus and albudinus, along with the stream of the Anno Novus, and he distributed to them a very large number of beautifully decorated basins. He attacked the Fucine Lake no less in the hope of profit as of glory, since there were certain individuals who promised that they would drain it at their own expense if the fields uncovered were granted to them. After 11 years, partly by digging a canal, partly by digging through the mountains, he finished the project with difficulty, even though 30,000 workers were employed continuously without a break. He even gave a banquet. Oh no, that's the part I saved for later. So, the pieces of equipment you can see here are a stone carving of a capspan. This was found next to the Fucine Lake, or rather the tunnel. This worked by having the two ropes attached to it. They would be counterspooled so that when the capspan was turned, one rope would be lowered while the other was raised. And at the end of each rope, you'd have one of these copper buckets reinforced with soft iron. They would have been about 40 centimeters, or 40 decimeters cubed in volume. Now, there was an added bonus to having the counterspooling of the capspans. One, you only had to turn it once to raise and lower a bucket, including increasing the efficiency of the project. But you also, in some cases, had 100 meters of rope. So by having the one section of rope going down while the other came up, you would help balance the weight, because you could be adding an extra 15 kilograms to your job just operating the machinery. So we've looked at the tunnel. To control the flow of water into the tunnel, there were 3 insilae created or built. Now, the lake is out beyond this section of the diagram. The first insilae was designed specifically to prevent the flow of water coming from the lake. It was brought from the lake to the tunnel by the construction of a canal. Now, this was constructed to ensure that the water flow from the canal didn't undermine and weaken the rest of the structure. The center insilae was shaped like a hexagon here, was specifically used to control the rate of flow of water entering into the tunnel. So it had a very, very strong sluice gate built into it. And the final insilae here was used solely to direct the water down into the tunnel. And again, it, as with the first one, also had sluice gates to control the flow of water, but these were not designed for regulating the flow of water. These were solely for stopping the flow in the case of an emergency as need be. So, did the project work? Well, unfortunately, no. Not really. Well, not at first anyway. When the time finally came to let the water flow into the tunnel, it became immediately apparent that there were issues with the design. That's the center hexagon insilae, which we saw above, which is located here, was 5 meters too high. Now that would have meant that the volume of water that could have been drained from the lake wouldn't have even covered the cost of the construction of the project, of the tunnel at all. So the blame for this was placed squarely on the feet of Narcissus, our friend from earlier on. And his solution to the problem, if one was inclined towards conspiracy theory, you would think he would almost planned it. For rather than saying, all right, we'll take our time and sort this problem out correctly, he decided to drop a shaft at the mouth of the central Incili, build a tunnel behind the shaft to to prevent the water flowing into the center Incili, so that all of it would be directed down the shaft. This shaft then ran beneath the Incili, bypassing it entirely, where it would reconnect with the third Incili and flow down into the tunnel. Now this meant that there was only one sluice gate controlling the entire flow of water coming out of the lake. And this was not the one which was designed to control the flow of water. So when he'd when he'd completed the temporary works, he thought it would be a good idea to regain favor with Claudius by arranging a big party, building a pavilion at the mouth of the hexagonal basin, placing this pavilion on piles, raising it up above, so that they could stand at the edge and look over down into the shaft, so they could see the water coming from the lake and disappearing down into the earth. Unfortunately, when the canal was first opened, it broke the sluice gate, overturned the wall, washed out all of the piles beneath the pavilion, and very nearly killed Emperor Claudius along with his entire entourage. So, not the best idea. We have a couple of historical accounts as well. One from Tacitus. He says, about the same time, the mountain between Lake Fucine and the river Liris was bored through, and that this ground might be seen by a multitude of visitors. Preparations were made for a naval battle on the lake. When the sight was over, the outlet of the water was opened. The careless execution of the work was apparent. The tunnel not having been bored down so low as the bottom or middle of the lake, consequently, after an interval, the excavations were deepened, and to attract a crowd once more, a show of gladiators was exhibited, with floating pontoons for an infantry engagement. A banquet too was prepared close to the outflow of the lake, and it was the means of greatly alarming the whole company, for the water, in the violence of its outburst, swept away the adjoining parts, shook the more remote, and spread terror with a tremendous crash. At the same time, Agrippa availed herself of the emperor's fight to charge Narcissus, who had been the agent of the work, with avarice and peculation. He too was not silent, but inveighed against the domineering temper of her sex and her extravagant ambition. They kept it interesting. Cassius Dio, who lived roughly 100 years after the tunnel was built, gives us another account. Now this isn't first-hand, but it does have the benefit of hindsight. So they'll have a full understanding of the implications of what Narcissus had done. When the Fucine lake caved in, Narcissus was severely blamed for it, for he had been in charge of the undertaking, and it was thought that after spending a good deal less than he had received, he had then purposely contrived the collapse in order that his wrongdoing might not be detected. He furthermore desired to make an that's okay. So, did the project work? Well, up until this point, it's a yes and no situation, because while it did still manage to drain 6,000 acres of the lake, or 24 square kilometers, and the floods which would affect the area were restricted in their intensity. So, this is another plate from the Brise report, and it shows cross-sections of a sample of cross-sections from the Roman tunnel along its entire length Fortunately, it has most of the different ground conditions, so you can see these sections are where the tunnel passes through solid rock, and these sections are where it passes through clay and sandy areas. The one thing which is consistent throughout each section of the tunnel is its inconsistency with any of the other sections. The brick sections were used when passing through the unstable ground conditions and the tunnel required shoring up. They were made with a section of concrete along the base, brick to the sides, and a concrete arch over the top. It was uncovered during this survey that the quality of the construction was also poor within the tunnel itself. For instance, the post holes, which were left, there were post holes found within the concrete. Now these were leftovers from whenever the concrete was poured, and they would need to have been in place to maintain the concrete shape. Now after these were removed, the post holes weren't filled in afterwards, they were just left as they were. So this is where you start to see the cowboy builders taking effect. Now again, the execution of this tunnel does not reflect on its design, because when examining the rock sections, the sections of the rock sections of the tunnel beneath Mount Salviano, which was the hardest section of the tunnel to align correctly because it was so far from the surface, the alignment was pretty much spot on. They got it right. So again, it wasn't due to the engineer who constructed the tunnel. It was very much due to the upper management. I was able to model the tunnel using a computer program called Swim. And using that, I was able to generate different flow rates through the tunnel itself. So the blue line along the base is the bottom of the tunnel, and the green line along the top is the roof of the tunnel. Again, you have to remember that this is highly compressed along its length. But what that does provide for us is a clear image of where the design of the tunnel was, or the construction of the tunnel was completely wrong. There are 9 sections along its length where the flow of the water had to go uphill. Well, the water can't flow uphill, but the base of the tunnel rose rather than fell along its length. So this is a simulation of the tunnel as it was built. The top one shows the conditions of the tunnel when the water flowing through it was done in an uncontrolled manner. Now this would have occurred when the floodgates were broken during Narcissus's party. This blue line here represents the height of the water above the roof of the tunnel. What this does provide, however, for us is a maximum capacity of the tunnel and uncontrolled flow rates. So that gave us a 9.16 cubic meters per second, which isn't small, but the tunnel couldn't handle those flow rates. This one provides us with controlled flow rates where the surface of the water did not exceed the roof of the tunnel. And it was able to manage 3 cubic meters per second, which is only 33% of the tunnel's maximum capacity. Now, had the tunnel been built as they were more than capable of building it, you would have ended up with a profile looking more like this. Admittedly, this is a mathematical design, so it's beyond perfect, beyond what could have been done. But it does give us an estimate of 14.26 cubic meters per second. And that's operating at a 70% capacity of its total capacity. The difference in volume of material between this tunnel and this tunnel are 8,247 cubic meters. Now, again, that alone won't account for the difference in flow rates between the optimum tunnel and the built tunnel. It again comes back to the poor design, or not poor design, the poor construction, with the 9 sections of upward flow within the tunnel itself. This being the major choke point along its length. This is a photograph of one of the Cunaculi del Caballo, located on the Antonine Plain. I'm including this, I probably should have put it in earlier, but I'm including this to illustrate the much more shallow gradient that would have been taking place within those Cunaculi. And this would have been specifically used for air circulation and, in some cases, the removal of excavated material. So this is what the lake looks like today. It has been completely converted into agricultural land. Now, while there is evidence to show that the Romans never fully intended to drain the lake, had they built the tunnel correctly, it is highly likely that as time went by, more and more of the lake would have been drained. As with the rise of Christianity in the later Roman Empire, the relevance of the god Fucine would have passed, removing that restriction on the size of the lake. Now, to put again the scale of what could have been available to the Romans, you really need to look at this image, which is, here is the lake, here is Rome, that's the width of Italy. It was an absolutely enormous area. And this could have been a real breadbasket right in the heart of Rome, or right in the heart of Italy, which would have spared the Romans deep dependence on the grain shipments coming over from Egypt, and may have helped prevent the bread riots which impacted the fall of the Roman Empire. So it is a bit cliche to say that it could have changed the course of history, but things could have been a little different. Thank you very much.